Mixtures of gases. A lot of gas samples are actually mixtures rather than a pure compound or an element. Dry air. So the air in the classroom is a mixture of gases: nitrogen, oxygen, argon, carbon dioxide, and a few other things. So it's mostly nitrogen, 78% by volume, 21% by volume oxygen, 0.9% by volume argon, 0.04 of carbon dioxide, and then much less than 0.04% of a variety of other gases. Sometimes we can treat a gas mixture as though it were a single gas, because when we measure the pressure, the volume, and the temperature of a gas, those all depend on the number of moles of gas molecules. It doesn't matter what the particles are. So we can calculate the total number of molecules even though they are different molecules. And that's because gases behave independently. We're going to talk later in the chapter about the theory of gases called kinetic molecular theory, and that explains why this works. But now we're dealing with laws, just saying what happens. So in a mixture of gases, each individual gas is going to exert its own pressure, and that's called a partial pressure. The partial pressure for a single gas, N, can be calculated from the ideal gas law. So the pressure of gas N is equal to the number of gas moles times RT over V. R is a constant. The temperature and the volume are going to be the same for all of the gases in that sample. If you have a 1 liter container, all of the gases are occupying 1 liter of volume. John Dalton, who's the same guy who came up with Dalton's atomic theory, also has Dalton's Law of partial pressures. If you take the partial pressures of all the gases in the mixture, they will add up to be the total pressure of that mixture of gases. This is a little bit like how, let's think of an elevator. You've got an elevator and 5 people go into the elevator. You know, if you ride the elevator here, it says the conveyance, it calls it a conveyance. And there's a maximum weight limit, right? So people get into the elevator. Each person exerts their own weight, their own force in the elevator. The total weight of people in the elevator is just the mass of each individual person all added up, right? And so that's how gas partial pressures work. Each gas exerts its own pressure. The total pressure in the container is just the sum of those partial pressures. There's another one of those written out derivations that can make your eyes glaze over. What is this talking about? This is just trying to show you something. So this is Dalton's Law of partial pressures. The total pressure equals the pressure of gas A plus the pressure of gas B plus the pressure of gas C, blah, blah, blah. Well, what does the pressure from gas A equal? It's the moles of A times RT over V. The pressure of gas B is the moles of B times RT over V. There's a pattern here. Each of these has the same factor, RT over V. So if we factor that out, then we have moles of A plus moles of B plus moles of C times RT over V gives us the total pressure. So the total number of moles of gas times RT over V is equal to the total pressure. We can figure out partial pressures of gases from mole fractions, or vice versa. If we know the mole fraction, we can find the partial pressure of a single gas. So if we take the ratio of the partial pressure of one of the gases to the total pressure of the entire mixture, the pressure of a single gas is equal to the moles of that gas times RT over V, and the total pressure is the total number of moles times RT over V. And so these factors cancel out, and we're left with moles of A over total number of moles. That's called the mole fraction. If you multiplied by 100, it would be the percent by moles. And that's given the sign chi. Chi of A is the moles of A divided by the total number of moles. The mole fraction can help us to relate the pressure, partial pressure of A to the total pressure of the gas. So here we're taking this side and rewriting them down here. And then we're rearranging that, multiplying both sides by P total, so we get PA equals NA over N total times P total. And then we're recognizing that NA over N total is equal to chi A. And so the partial pressure of a gas is equal to its mole fraction times the total pressure of the gas. And some of you may think, oh, that's really cool. And some of you may think, what the heck is she talking about? Well, there it is. I'm not going to make you derive that on an exam. So partial pressure of a gas in a mixture is its mole fraction multiplied by the total pressure. So that's what we just said and derived on the previous. And so if you don't remember how to derive that, you can just memorize the equation. That's the guy right there. So the mole fraction is equivalent to the percent by volume divided by 100, because the volume of a gas is proportional to the number of moles. So if we look at that composition of air, nitrogen is 78% of the air. So its mole fraction is 0.78. So if we want to find the partial pressure of nitrogen in air, we take the mole fraction times the total pressure. Normal atmospheric pressure is 1 atmosphere. 0.78 times 1. The partial pressure of nitrogen is 0.78 atmospheres. Here's an example. To prevent the presence of the air, noble gases are placed over highly reactive chemicals to act as inert, blanketing gases. A chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15.0 grams of neon, and 35 grams of krypton in a piston cylinder assembly at STP. Calculate the partial pressures of each gas. So we have a gas mixture. We want the partial pressure of each gas. There's two laws, two equations that we'll be running into. The total pressure for this one equals the partial pressure of helium plus the partial pressure of neon plus the partial pressure of krypton. And the other one is, I'll just do the first one. The partial pressure of helium is equal to the mole fraction of helium times the total pressure. So those are our two options for equations. Since we're trying to calculate the partial pressure of each gas, we're given mass information, but we could convert that into moles. So we're going to need this second equation. What we need to do is find the mole fraction of each of the gases. So this involves some calculating. 5.50 grams of helium. That's not an H. Helium. And we look up the molar mass of helium. 1 mole per 4.003 grams. .5 divided by 4.008. 1.37 23 moles. That's the moles of helium. We got to calculate the moles of the neon. 15 grams of neon. Neon is 20.18 grams per mole. So 15 divided by 20.18. Try that again. 0.743. I'm going to add two more places so that I don't have rounding errors. And then my last gas is krypton. 35 grams of krypton. 83.80. So 35 divided by 83.8. 0.41766 moles. We need mole fraction. The mole fraction is the moles of gas you're interested in divided by the total number of moles. So we need to find out what the total number of moles is. We need to add these guys all up. So N total 1.3723 plus 0.74331 plus 0.41766. 2.53327. Did I do that right? Anybody? Okay. Significant figures. If we keep track of them as we go along, I think it's a lot easier. Here we're adding these numbers. This one has 2 decimal places. That's where the uncertainty is in the second decimal place. This one is third decimal place, third decimal place. So then this number would be rounded to the second decimal place. So mole fraction of helium is going to equal the moles of helium divided by the total moles. (1.3723) divided by 2.53327. 0.54171. This is moles and moles, and so the fraction is unitless. I need space. So we don't need to look at that anymore. I think we can remember what we were doing. So the partial pressure of helium will be the mole fraction of helium times the total pressure. Oh, what was the total pressure? Was it at STP? It was at STP, wasn't it? Yeah, so then that's 1 atmosphere. That's not what I wanted. The pressure of helium is the mole fraction of helium. Well, I already have that written up there. 0.54171 times the total pressure. Well, at STP is 1 atmosphere. That is defined, and so that's exact. So our pressure of helium will be 0.542 atmospheres because we need to round up. That's the partial pressure of helium. It's a lot of little calculations, isn't it? Good luck doing this one in your head. not showing any work. It really helps if you write stuff down in an organized manner and be able to look at it. Okay, so here's my moles of neon. So the mole fraction of neon coming down here is moles of neon, 0.74331 divided by 2.53327. I can't just turn the page. Mole fraction of neon is going to be 2.53327. 0.29342. Again, times 1 atmosphere. And so my partial pressure there is 0.293 atmospheres. There's 2 ways I can find the third one. I can do the same thing. I can take the moles of krypton, divide by the total moles to get the mole fraction, and multiply it by the total pressure. Or I can say, well, these 2 numbers plus this unknown pressure must add up to the total number of atmospheres. And so I can actually figure this one out by difference. I could do that with the mole fraction too. But 1 atmosphere minus 0.542 atmospheres minus 0.293 atmospheres. .164. Now, ideally, I wouldn't have used the rounded ones. I would have used these. Any questions? That's kind of a booger, isn't it? No questions. Here's another one. Sample of hydrogen gas is mixed with water vapor. The mixture has a total pressure of 755 torr. The water vapor has a partial pressure of 24 torr. What amount in moles of hydrogen gas is contained in 1.55 liters of this mixture at 298 K? This is one of those ones you kind of have to think about for a minute. So we've got total pressure of 755. So maybe let's write that down. P total, 755 torr. Partial pressure of the water is 24. P H2O is 24 torr. We need to know the number of moles of hydrogen gas. We're given a volume and a temperature. Volume is 1.55 liters. Temperature is 298 K. We're trying to find the number of moles of hydrogen gas. Well, what's an equation that we've used to calculate moles of a gas? Yeah, we can rearrange the ideal gas law, PV equals nRT, and N equals PV over RT. We have the volume, we have the temperature, we know what R is, What's P? We have to subtract. So this is using Dalton's law of partial pressures. The pressure of the water plus the pressure of the other gas in the mixture, the hydrogen, has to equal the total pressure. So P total equals PH2O plus PH2. So the pressure of the hydrogen equals the total pressure minus the pressure of the water. So that's 731 torr. That's not a good unit, though, for our calculation. So let's put it into atmospheres. Let's divide by 760. 0.96184. Now we've got pressure, volume, temperature, and R. We can calculate moles. So pressure 0.96184 atmospheres. Volume was given to us as 1.55 liters. R is fast becoming a good friend. And then the temperature was given as 298 Kelvin. So I'm coming up with 0.0610 moles after rounding to 3 sig figs. Any questions? Did you come up with that? This is not unlike what some of your papers look like on your labs and written portions of exams. Can you see why I like you to put a box around your answer? It just makes it jump out. Then if I need to, I can go look at all the other stuff. But this is the answer. If the answer's right, I don't have to look at the rest of it. Deep sea diving. We talked a little bit about diving at the beginning of the chapter. So when a diver breathes compressed air is at a higher pressure. Then you get an abnormally high partial pressure of oxygen in your lungs. And then you get higher concentration of oxygen in your tissue. You might think, well, oxygen's good. We need oxygen to live, and oxygen is good. But anything at too high of a level is toxic. And so oxygen toxicity occurs somewhere above 1.4 atmospheres of oxygen. 0.21 is ideal. 0.21 atmospheres, that is air at sea level. Our bodies are really, really good at functioning under those conditions. If you get too much oxygen, you'll be fine for actually quite a while, but if it gets to an extreme, oxygen is toxic. We're much closer to the oxygen starvation level. It's also called hypoxia, low oxygen. When the oxygen levels drop too low, that's when you get lightheaded, you start to feel dizzy and weak, and you could pass out and die. So at high elevations, the air pressure is lower and the oxygen pressure then is lower, and you can have elevation sickness. When you are flying in an airplane, you're going up to very high elevations, and so they pressurize the cabin so that everybody doesn't pass out. When you're breathing compressed air, you're also increasing the partial pressure of nitrogen. Nitrogen composes 78% of the air. And so nitrogen can also be toxic at high levels. If you get above 4 atmospheres of nitrogen, you can experience nitrogen narcosis, or sometimes called rapture of the deep. It has symptoms similar to alcohol intoxication. You may think, well, that's not such a bad thing. If you're several meters below the surface of the ocean, is that a good place to be drunk and do stupid things? No, it isn't. At the surface, where the total pressure of air is 1 atmosphere, we get a nitrogen pressure of 0.78 and an oxygen of 0.21. 30 meters below, the pressure of the gas has to be 4 atmospheres in order for you to be able to breathe. Otherwise, you wouldn't be able to expand your lungs and breathe. And so there you get a pressure of nitrogen of 3.12 atmospheres. This is getting up close to this limit of 4. The oxygen pressure is 0.84, which is still manageable. So what some deep sea divers do is they breathe a special mixture of gases instead of just compressed air. And one of them is called Heliox. It's got helium and oxygen. Breathing helium doesn't have effects like that on the body that nitrogen and oxygen do, although it does make your voice high and squeaky. But you're underwater, so nobody can hear you anyway. So a diver breathes a Heliox mixture with an oxygen mole fraction of 0.050. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? You need a partial pressure of oxygen to be 0.21 atmospheres. So this Heliox mixture is great for breathing at high pressures, but not good for breathing at normal pressures. And that's why, it's always fun at a party to untie a helium balloon and take a big lungful of helium and then talk like Mickey Mouse, right? That's fine as long as you're not breathing that continually, because if you breathe that continually, you're not going to get enough oxygen and you'll pass out. So the mole fraction, 0.050. So that's chi of O2, 0.050. There's no units on that. We want the partial pressure of oxygen to be 0.21 atmospheres. We're not going to use Dalton's Law of partial pressure. We're going to use this guy, the partial pressure of the oxygen is equal to the mole fraction of the oxygen times the total pressure. We want to know what the total pressure is. So we're going to rearrange this. Total pressure equals the partial pressure of oxygen divided by the mole fraction. 0.21 atmospheres divided by 0.050. 4.2. So for this particular Heliox, you need to be breathing it at a pressure of 4.2 atmospheres to not pass out. So this is where you'll see a diver with 2 different tanks. One is compressed air and one's Heliox. And as they go down, they gradually switch from the compressed air to the Heliox. And then on the way back up, you switch the other way. That's why they make you go to classes before they let you do that. Gases are really great to work with in some ways, and they're really hard to work with in other ways. One of the things that's difficult about them is they won't just stay in a beaker, right? Liquids will just sit in a beaker. Maybe they'll evaporate, but it's not a big problem. Gases, you leave them in an open container, they fly out and they go all over the place. So when you've got a gas that you're generating, how do you collect it? We often collect it by having it displace water from a container. What happens then is that in that container we have the gas we're collecting, but we also have water vapor because it's in contact with the liquid water and water evaporates. And so we have a partial pressure of water and the partial pressure of the gas we're interested in. The partial pressure of the water is called the vapor pressure. It's the vapor pressure of water, but since that's the liquid we usually use, we don't even specify the water. That vapor pressure depends only on the temperature of the water. And so people have measured it, and you can just look it up in a table. So that's pretty nice. Here is such a table. So at say, a temperature of 20 degrees Celsius, which would be a cool room, the partial pressure of the water, the vapor pressure, is going to be 17.55 millimeters of mercury. As you increase the temperature, the vapor pressure of the water goes up. When you get to boiling, the vapor pressure of the water is equal to the atmospheric pressure. So when you need vapor pressure of water, you go look it up in a table. You do not memorize this. I don't remember those. The only one I know is at boiling point, it's 760. Come on. My iPad is misbehaving again.